Everyone, so today we're going to talk about a new topic, work, and it is very closely related to energy. Now, when we talk about this, one thing I want you to keep in mind is last unit when we did impulse and momentum. So, impulse is the change in momentum of a system. Work is the change in energy of a system. So, they're quite similar in a lot of ways. So, we measure work in joules just like energy, and our equations for work are this: work equals force times distance, which equals the change in the total energy of the system. It's really important to note that force and displacement have to be in the same direction. That's not 100% accurate, but for our purposes, they got to be in the same direction. So if we have a 20 Newton force eastward and it moves it a distance of 5 meters eastward, work equals force times distance, 100 newtons of work was done. Another unit for work is newtons times meters. Now, what do I mean by this same direction? Well, check this example out. If I have a bag and I'm walking with the bag, I apply a force upward because I'm holding it, but I'm moving sideways. Those two vectors are perpendicular to one another, so there is no work done. If I lift a bag straight up, though, if I take it and lift it straight up, I apply a force upward, and now it's moving upward. Force and displacement are in the same direction, so the work is not 0 joules. Okay, so that's kind of what I'm talking about there. In this class, if it doesn't mention the, excuse me, uh, if it doesn't mention the direction, you can kind of assume that they're going to be in the same direction. All right. So the area under a force versus displacement graph represents the work. So the two areas here, you have a rectangle, 30 joules, you have a triangle, 15 joules. That's how much work is done there. So we had a couple activities here, and the point of these two activities, numbers 8 and 9, were for you with your group to figure out that work was the change in energy. I didn't tell you, if you recall, I didn't tell you that when at the beginning of class. I did this time, but in class I didn't tell you. So the first question was, okay, so we're lifting up an object. So how much force is required to lift it up? Well, the amount of force required to lift up an object is equals to its weight. So mg, 147 newtons. What was the initial and final potential energy of the object? It looks like it was 0 joules because it was at ground level, 294 joules because it was a little bit higher up. How much work was done? That was the force times distance, 294 joules. So clearly there's something going on here that these two are related. And what we deduced was that work was equal to the change in potential energy. Looking at number 9, it's a little bit different. We have a cart that's moving, and it's pushed with a force of 5 newtons. So the first thing you have to do is find the acceleration of the cart, which we just did with Newton's second law, A equals F over m, and we get 0.25 meters per second squared. Then using this equation that you recall from last class, we find that the final velocity is going to be 2.45 meters per second. It's sped up a little bit. The initial kinetic energy of the system using the initial velocity was 40 joules. The final kinetic energy of the system using the final velocity was 60 joules. Okay, make sure you do these calculations to make sure you can get these numbers. And the work done on the system by the force and the displacement was 20 joules. So you can kind of see this a little bit clearer here, that the work is equal to the change in kinetic energy. So which one is it? It's actually both of them. The work done on a system is equal to the change in total energy of the system. Now, maybe it's worth noting that it's not just, remember, total energy is potential, kinetic, and Q. Next class, we'll talk a little bit about how work can increase Q in the system, heat energy or internal energy.